All right, so we're going to copy the data from Regression 5A into Excel. And again, I'm going to copy the data plus something outside the table to preserve the formatting. And this is simulated data. I created an algorithm that simulates this data, so everybody that does this will have a unique solution set. It's not actual data. I need to bring this down here. There we go. I'm going to go ahead and delete row 1. And then I'm going to word wrap. There we go. So this right here is the lobster price. And we got customer income and the quantity demanded. Yep. I'm in the class. Okay. So we have to do some descriptive statistics. Let's go to data analysis. So we're going to click the data tab up here, and then click data analysis in the ribbon. And then you can do descriptive statistics right here. See that? This is a fast way to get the means. And then we'll just hit OK. I'll put the output. I'm going to click on output range. Click on that white box right there. And then I'll put the descriptives right here. And then group by columns. Yep. Oh, we need a. So group by columns, click labels, and then hit OK. Input range. Oh, I thought I did that. Okay, so we got the input range. It's grouped by columns. Labels in the first row. Output range. Specify that. Huh. All right. Oh, summary statistics. There we go. Huh. That's weird.
I think your when you first copied your data for your output range. Yeah.
All right. There we go. All right, cool. And then we have the means right here, right? We have a bunch of other stuff. So I'm going to go ahead and delete the other stuff. I'll move the mean down here. And then we'll there's probably a fast. I mean, we could probably have done this a little faster by just coding it, right? But it's kind of fun to. I rarely ever use that descriptive statistics thing. So then we'll center this. I feel like I'm in slow motion today. We'll move this over here like this. Mean. Make it nice and compact. We'll word wrap this too. There we go. That looks pretty good. So it looks like my mean is 75 for lobster. So this Blue Lobster Bar and Grill is selling 75 lobsters to its customers on average during the time period of this collection of data. The mean price of lobster was $34.79. And then mean customer income, $2,066.29. This is probably, now with inflation, this is probably like weekly income with all the inflation that we've had. All right, any questions on that? That's pretty easy, right? Now we want to perform an multiple regression analysis. We want to know how much quantity is going to be demanded by our customers, given the lobster price and customer income. Okay, so quantity demanded is our Y variable, and it depends how much our customers purchase, depends on the price and their income, right? So we'll go back over
Sir,
here. Yep.
what did you get for the mean and to get right there? What'd you type in right there? Or something there about?
Oh, to get this?
Yeah.
Oh, did you come in a little late?
Yes, sir. 6 minutes to be exact.
Yeah.
Just show me the equation.
I didn't use an equation, but if you wanted to use an equation, you could just do this. What I did is I used data analysis, and then I chose descriptive statistics, and then I deleted
Hold
things I
on.
didn't need.
You said data analysis?
Yeah, but I can show you something that's probably faster. So
Data.
where you want the mean of quantity demand, you can just type equal average, right? And then you can just highlight
because
right there.
Yeah, because that's what I just did right there.
Yeah.
I did the same thing to get the mean of quantity of lobster, but yeah. Maybe hold on, let me try something else. Make sure I'm doing this right. Okay, now I've got it right. Thank you.
Okay, cool. Yeah. Well, limited to 2 decimal places, but you can also use the data analysis tool and choose descriptive statistics. And then this is your input range. This is where we put the output. And then summary statistics, you want to choose that option. And then make sure you choose labels because we included the labels, and then hit OK. And make sure it's grouped by column. And then I'll give you a bunch of other stuff that we didn't need, but it might be just easier to write equal average, right? And once you have that one, you can just drag it across. Right. Cool. So I'm going to color coordinate this. I'm going to color code this. I'm going to make this yellow. I'm going to make these 2 blue, light blue. And the reason why I did that is because I want to make it explicit that we want to predict quantity demanded. How much our consumers want to buy from us, how much they're demanding from us, right? We want to predict that. Why do we want to predict that? Because we need to know how much lobster to buy from the fresh market each day, right? So we can guesstimate it. We can guess using intuition. But the thing about lobster is that you want to buy it fresh and cook it fresh, right? Buying lobster and it getting old on you ends up in a soup, right, called lobster bisque, or it ends up in mac and cheese, and you'll make more money off lobster if you can sell it live and fresh, right?
Should
All
we
right.
round the quantity of lobsters to a whole number, or if we got a decimal for that answer, should we put it in as a decimal?
Yeah, I guess I said round at 3 decimal places, but 2 seems to work right here. If it rounds as an integer over here, you can just enter it as an integer, so you don't have to worry about it. Yeah, if it's an integer, you can put it in as an integer, or you can put it in as 75.000. Right? Okay, so let's go ahead and run the regression. again, we want to predict this value using these values, right? So let's go to data analysis, and then we're going to find regression down here. Now, does everybody have this tool? Everybody has this tool, right? Data analysis tool.
Hang on, what'd you have to pull up
Yes.
or something?
Yeah, you want to pick. You want to click on data right here, the data tab,
Okay.
and then you should see data analysis over on the right.
Oh boy.
You don't see it?
Apparently I don't have it.
Okay, so do you have Mac or PC?
PC, sir.
Okay, so click on File right here. Whoop, let me close this
Got
out.
it.
Yeah, click on File. Go down here to Options at the bottom. Options.
Check.
And then you want to go to Add-ins.
I'm there.
Okay, and then down here it says Excel add-ins. Hit Go. And then make sure your analysis tool pack is check marked.
Analysis tool pack. Standard or VBA?
Just standard, yeah. And then just hit
Okay,
OK.
now I have it.
Yeah, there it is, right? Cool, awesome.
All right, you said regression.
Yeah, so we're going to click data analysis. We're going to find regression, hit OK. Now, I color coded this, right? Because I want the Y to be explicit. We have one Y and one or more X's, right? One or more things are going to explain the thing that we want to predict. So I'm going to click on this arrow to the right of the white box on the Y input range. And I'm going to highlight the data and the name quantity demanded. Okay. Then I'm going to do the same for X, except I'm going to capture both of them at the same time. So I'm going to start at lobster price and then go down to the final customer income. You want this dashed green line around both columns. Okay. And then you want to click on labels and output range. After you click on the output range, click on that white area right here. And then click down here. You only need to click on one cell. I don't think we need residuals. Oh, we need residuals. So let's go ahead and click on residuals too. So let me know if you have that all set up. I have my Y in column B and I have my X variables in column C and D. And you can see this goes from B1 to B9, B1 to B9. And then this says C1 to D9, right? C1 to D9. And then labels, output range, residuals. And I'm putting my...
And yeah, what's your output range?
I'm just putting it right below my means. So I'm putting in an A16 down here. And then once you have all that, you can click OK.
Uh-oh. Regression input range contains non-numeric data.
Okay, let me click OK. When you're done, it should look like this, right? Let me have you share your screen, Craig.
One moment. Okay.
We put quantity demanded in the Y range, right?
Oh yeah, you want to move your mean down just a little bit. Yeah, pull that down. Just pull it down. Yeah, you don't want to include it. And I made sure I'd use one color. First of all, I'd use one color for the X. So I'd go back and just choose one color there. Yeah. Oh, and then get rid of that. Yeah, here, right there, that blue box right there. No fill. Yeah.
Okay. Now, let's see.
Oh,
Data.
now this is the reason why you have a problem. See the empty space in B2?
Now
Move,
I do.
yeah, move the quantity demanded. Yeah, there you go. Now you gotta move the other ones up too.
Okay.
Yeah. You gotta move those up. That's the reason why you had a problem right there. Okay.
All right.
Now it should
Now
work.
then.
Yeah.
Okay. Let's see.
Oh, then yeah, reset that. There you go. Excel does not do well when you're missing values.
Yeah.
C1 to D9. Okay, that's good. Yep. There it goes.
All right. I'm
Good.
gonna stop sharing.
Okay. Okay, so the next thing I want to do is I'm gonna click and hold and highlight all the decimal values in my table. Right now I'm holding down the control button. I'm gonna highlight these values and all these values. I'm gonna change the number of decimal places once for all of it, right? I'm gonna go up here to home, number, and then change the number of decimal places to 3, right? I'm also gonna widen column A so I can see the names of the stuff. There we go. Okay. Now it's just a matter of typing the numbers in. Okay, so real quick, I mentioned this last week. I don't like how Excel calls this residual. I'm gonna change the name of it to for error, or sorry. I don't like the name residual. So I'm gonna change the name of this to error. Because this the sum of squares, some of the sum of squares error, estimated error, right? So this is called the SSE, and this right here is called the SSR. So by calling it residual, you can confuse people, right? So the first thing I always do is I change that to error. And the next thing I do, I don't like using significance F here. So what I like to do is I like to use p-value. This is the p-value of the statistic. And that's the F statistic right there. Yep. F statistic is just the ratio of these two. If I divide this by that, I get the F statistic. The mean square due to regression, mean square due to regression is just the sum of squares regression divided by the degrees of freedom. The mean square error is just the sum of squares error divided by degrees of freedom. The sum of squares regression divided by the total sum of squares, these two, that ratio is the R square, and it's pretty high in this example, right? And then one last thing, when you divide each of these by its corresponding standard error, you get the t-stat. Okay, so this divided by that is this t-stat. This estimated slope coefficient of lobster price divided by the standard error is this t-stat. This estimated slope coefficient of customer income divided by standard error is that t-stat, right? So that's some quick explanation of what these numbers are, or how some of these numbers are calculated. And then down here, what I'm going to do is I'm going to copy this. I'm going to take these two columns here. This is the predicted quantity demanded right here, right? This is the predicted quantity demanded, and these are the residuals or estimated errors. I'm going to copy them. I'm going to grab this and put it up here next to my data. I'm going to word wrap that. Okay. I'm going to shrink the number of decimal places to 3. And I'll show you how Excel calculates these things, right? So this is what we observe in the quantity demanded when we have that price, that customer income. This is what we predict. This comes from our model. This again is what we observe when we have that lobster price and that customer income. This is what we predict from our model, et cetera, et cetera. So these are pretty close in value to these, right? And the closer they are in value, generally this will rise, right? The R-square will rise. If these are identical to these, then this will be 1. Okay. If this is 1, this error here, sum of squares error, will be 0. These two would be 0, right? And this would be really extremely large, right? Because anything divided by 0 would be really extremely large. Now, how do we come up with these numbers here? Real quick, let's just do one of them real quick. I'm going to take lobster price. I'm going to multiply it by the slope coefficient for lobster price. Yeah, multiplying the lobster price by its slope, right? Then I'm going to just add, right? I'm going to add that to what? I'm going to multiply this customer income. Right? So I'm taking the lobster price, multiplying it by its slope coefficient. I'm going to add that expression to customer income times its slope coefficient. And then I'm going to add the intercept. Right? So I got lobster price. So I had the lobster price times its slope coefficient. I got customer income multiplied by its slope coefficient. I add those two together, and then I add that to the intercept, right? So I'm plugging numbers basically into an equation, right? And that's called deploying the model, right? You can deploy the model to help you determine how much lobster you want to purchase for the night's menu, right? So I'm going to freeze. I'm going to put a $sign between the B and the 33. B33 down here for me is lobster price coefficient, right? And I'm going to put one between the B and the 34. And for me, B34 is the customer income slope coefficient, the green one, right? And then the last thing I'm going to do is I'm going to put a $sign between the B and the 32. B32 is the estimated intercept of this linear equation, right? Now, why did I do that? Because I'm going to pull this down, see? So now I'm taking the second observation of lobster price and customer income. I'm multiplying the lobster price in the second observation by the lobster price coefficient, right? But I'm going to add to that the customer income times the customer income slope coefficient, B34. Then I'm going to add to that the intercept of my equation, right there, 102.436, right? And then I can just drag this down, and notice the values won't change, right? The values don't change. Okay. Everybody see how we predict the model? So if tomorrow the lobster price is $37 and customer income is $2,900, right? I don't have an observed value here, right? But I can use the model, this model here. I can use the model to make a prediction about what I expect quantity demanded of lobster to be if my lobster price is $37 and my customer income is $2,900, right? You see that? This is a
Can you
prediction.
bring that equation back up one more time?
Yeah.
What was the other ones? As in the 37 to 2,900?
Well, these are just numbers that I made up, right?
Oh.
Suppose tonight or today, I'm gonna have a price of 37 on the menu, right? Because anytime you buy lobster, it usually doesn't have a price on the menu and it just says market price. So I'm setting today's price at 37. Maybe that's because I bought it from the fresh market for 25, right? And I need a bit of a markup, right? Otherwise, if I'm not making any money, I'm not going to be, my doors of my restaurant are going to be closed pretty quick, right? So maybe I bought it for 20 and I want a $17 markup, right? So if I set the price at 37 and I believe my customer's income will average $2,900, then I got to buy roughly 73 lobsters, right, from the market, right? So again, what am I doing here? I'm just taking this 37 and I'm multiplying it by the slope coefficient of lobster price, right? This middle number right here, right? And then what am I doing? I'm taking the customer income here, right? And I'm multiplying that by the customer income slope coefficient, the green box. And then what am I doing? I'm adding the intercept to it, right? I'm adding the intercept to it. So this is my model right here. This is my model. Okay. Now, what about the residuals? How do we get the residuals? I like to call them estimated errors. I'll just call them errors, but they're estimated errors, right? All you do is you take your predicted value. Let me do this. Oh. So you take your observed value, right? Oops. Take your observed value, what we observed in reality, minus what our model predicts for that price and customer income. All you do is just subtract the two. See that? You can do that for the rest of them. Notice the numbers do not change, right? The numbers do not change. So again, my observed value minus what my model predicts. My observed value minus what our model predicts, et cetera, et cetera, et cetera, right? My observed value minus what my model predicts for these two values, given these two values, lobster price and customer income. Okay. Now I can't calculate the error here, right? I can't calculate the error here because I haven't observed the quantity demanded, right? So I can't calculate that error. All right. Now, another thing that Excel does in its output, it has degrees of freedom to the left of the sum of squares values. These are the sum of square values. Now, what are sum of square values? Let's just look at error, for example. How do we get 23.759 here? Well, all I do is I square the errors, right? Square the errors, square the negative signs. Square all the errors, right? And then what? Sum of squares. I sum these squares. So the sum of squares of the errors, right? That value is that value right there. See that? So that's what sum of squares means, right? We square a bunch of stuff, then we sum it, right? Okay, so we got to fill in our information here, right? We got to fill in our information here. The degrees of freedom are 2, 5, and 7. Now, why 2? Well, the regression degrees of freedom, the regression degrees of freedom are 2 because we're estimating 2 slope coefficients, right? We're estimating 2 slope coefficients. That one and that one. So that's why it's 2. We have 2 x variables. We have 2 x's, lobster price and customer income. That's why that's 2. Now, why is the error 5? Well, we have 8 observations, right, total. We have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 total observations, and we estimated 3 parameters, right? We estimated the intercept and these 2 slopes. So 8 observations, right? Each row is an observation. So we had 8 observations minus 3 parameters that we estimate. 8 minus 3 is 5. Okay. So let's type in our sum of squares. I'm going to copy and paste. F statistic is pretty big. We expect the F statistic to be close to 1. And I don't think I have a p-value out there. Yeah, I don't have a p-value out there. If these two things, if the mean square due to regression and the mean square error are equal, the F stat is equal to 1. And what that means is the variance from the predicted y's, if these two are roughly the same in value, what you're going to see is the variance in these things are going to be pretty close to the variance in these things. Right? That's the intuition behind it. What we want to observe is a big variation in this and very little variation in that, right? We want our errors to be small and consistent, right? We don't want a lot of variance in our errors, right? If we have a lot of variance in our errors, then we're probably missing some things that help predict quantity demand of lobster. So this right here measures kind of like the variance in our regression. And then this one here measures the variance in the errors. Okay. So let's continue typing in our information. We're copy and pasting it. our intercept, the slope coefficients, the corresponding standard errors, and then you take the ratios of those pairs, you get the t statistics. Hit enter to see if we got. Let's say we got everything right so far, right? Okay. And again, this is our model right here. The constant, the lobster price slope, and the customer income slope. That's our constant. Our errors are the difference in what we observe and what we predict. Our model. A negative error means our predicted value exceeds our observed value. A positive value means our observed value is greater than what we predicted. And a good example of this, an intuitive example of what's going on here with the errors, is in the draft, the NFL draft. The model is used to figure out which college player is going to be the best player as a rookie, right? The best player for the next 10 years, right? We use a model to make those predictions, right? But what we predict in the draft is not always what we observe on the field. For example, Tom Brady was a 6th-round draft choice at quarterback from Michigan. So NFL football teams didn't think he was going to be all that great. The model didn't predict that he would be the GOAT, the greatest of all time, right? What do we observe? Well, we observe that he was probably the greatest of all time at quarterback, right? So that's kind of how you can look at the predicted values. You can think of this as the draft order, and you can think of this as how their careers played out after they were drafted, right? Michael Jordan was a third pick in the draft, I think in '83, right? And he ended up being the greatest of all time in basketball. So Michael Jordan was even the first pick overall, right? So sometimes we get it right and sometimes we get it wrong, right? And the errors are measuring literally that error, right? The sum of the residuals, the sum of the errors, if you notice the sum of the errors is what? Sum of the errors is 0, which makes sense, right? Because this horrible prediction is offset by this excellent prediction, right? Here, our prediction was we predicted high, but we observed low, right? But that was offset by this, right? So for every bad prediction, bad being the predicted value is much higher than the observed value, we have the opposite, right? And those two things will offset each other. And so the sum of the errors is going to be 0, right? When we square the errors, like we did here, right, we squared them. We squared each one of these. And then we sum those squared errors. Get 23.759 in my model, right? Now you don't have to square your errors and sum them, because Excel does it for you right there in the output, right there in the regression output. 23.759, right? So you didn't really have to square each of these errors, right? You had to square these errors. You also didn't need to sum it, right? Because the sum of your errors in most situations is going to be 0. In most things that you do in your life, you do really well one day and you do poorly the other day. What is the error from the mean, right? Well, that day you did really well is going to offset that day you did really, really poorly, right? And those deviations from the mean, from what we expect, one's going to be negative, one's going to be positive, and they'll cancel each other out. So that's all that's saying right there, right? Is we have error, but those errors collectively cancel each other out, right? And this value equals the sum of squares error, right? That's why we call it sum of squares error, right? We sum the errors that have been squared. Yep. From the regression statistics table in the Excel output, answer the following. Now we're looking at this part of the table, right? Regression statistics. The standard error of the regression is this value. Now, how do we get this value here? Well, we're just taking the square root of the mean square error. If I take the square root of the mean square error, I get the standard error of the regression. You can think of this, right? This value here is a standard deviation. You can think of that right there, this value. You can think of this value right here as the standard deviation in the errors, right? We call it the standard error of the regression. Remember, we said this was what? We said this divided by 5 is the mean square error. This right here is the estimated variance of our errors, right? Okay, so we need to find the coefficient of determination. The coefficient of determination is just called the R square, right? So the coefficient of determination is the R square. And it is 0.928. And generally you want that high. Highest this value can be is 1. This can't get any higher than 1. Well, why is that? Because the coefficient of determination is the ratio of the sum of squares due to regression divided by the sum of squares total. Okay, it's that ratio. And the biggest that this can get is the total sum of squares. This can't get any bigger than 328. If this is 0, this will be 328.
How'd you get the standard error?
Oh, the standard error. That's just the square root of the mean square due to error right here.
Okay, hang on.
But it's also the regression statistics table. Right.
All right, thanks.
Okay. Now the biggest that this can be is 1. Because if you remember this right here, it's mean square due to regression. That's essentially the variance of these predicted values. Right? If the errors are all 0, right? If the errors are all 0, their squares are 0, the sum of squared error is 0, and the variance of this would equal the variance of that, right? So the variance of quantity demanded here is just the ratio of these two things. 328 divided by 7. The variance of the predicted values is the ratio of those two things. So the highest that this R square can be is 1, because if there's no error, this value in between the blue box and the red box, this value will be 0 if there's no error. If there's no error, then this value will be 328. Because what we'll have is the y-hats will all equal, the predicted y's will all equal the observed y's, right? So the biggest this can be is 1 here. Okay. And generally speaking, you want this to be a large value. Now, because we have two x values, we have two x variables, we don't interpret the R square in multiple regression. This is multiple regression because we have multiple variables on our right-hand side. We're using two things to predict one thing, right? When we have multiple regression, we have multiple x's. Here we have 2. In that situation, we can't interpret this. We have to interpret the adjusted R square. Which in my case is 0.899.
You put in the wrong number.
Right here.
No, oh, wait, sorry.
Yeah, you have to be really careful when you copy and paste from Excel to MyOpenMath. Sometimes you'll end up in the wrong box, right? So in simple regression, you interpret this value. In simple regression, you only have one x variable. In multiple regression, you want to interpret the adjusted R square because you have multiple x's, right? Uh-oh. What happened here? 928 doesn't work. That's weird.
Did you check R squared?
Yeah, it should be
Oh,
928.
yes, you did.
Yeah. Did you guys work?
Yes.
Yeah, that's weird. $33. Yeah, that should have worked. R square. 9.928. Oh, I think what happened is I probably put a space in there. Remember when I had that copy and paste mistake that you caught, Craig? You're like, oh,
Okay.
you put the wrong number in there. I think what I did is when I copied and when I accidentally copied here, then I had to fix it. I probably left the space in there because look how wide this is as opposed to these.
Yeah.
Right? Yeah. So this is the correct answer. I just got it wrong. All right. Yeah, that's the correct answer. It's just this box is pretty wide, so I probably put a space in there of some sort. Okay. Now, when you're interpreting the adjusted R square in multiple regression, or R square in simple regression, what you want to do is you want to multiply this value by 100, right? So I got 89.9. I'm going to convert the decimal to a percentage. So this adjusted coefficient of determination implies that 89.9% of the variation in the thing that we're predicting is quantity
Average
of lobster.
customer income and the, oh, go ahead.
Yeah, we're predicting the quantity of lobster sold, right?
Okay.
Yeah, we're predicting the quantity of lobster sold, right? So that 0.899, my adjusted coefficient of determination, which is equal to 0.899, implies that 89.9% of the variation in the thing that I want to predict, in this case, quantity of lobster sold, is explained by what? It's
Average
explained
customer
by,
income and the price of lobster?
yep, exactly. Yep, that's the model, right? Average customer income and the price of lobster. Yep. Now we want to do, the next thing we do after we interpret the R square is we want to do hypothesis testing. And we got to do two hypothesis tests for the coefficients. Beta 1, I got the first null hypothesis, beta 1 equals 0. What are we doing there? We're going to test whether this value here, right? We're going to use this estimate of beta 1. This right here is an estimate of beta 1, right? Beta 1's our slope of lobster price. And betas, Greek letters in statistics, we cannot know, right? We're not gods. So we cannot know these values. But we can use data to estimate them. And so we're going to use this value as an estimate of beta 1 to determine if lobster price is a predictor of quantity demanded for lobster, right? Now remember the T-stat, I'm going to delete this. T-stat is just this lobster price coefficient, slope coefficient, divided by the standard error, right? Now, our hypothesized value here is 0, right? Our hypothesized value is 0. So what I'm going to do here is I'm going to do beta 33 or B33 minus 0. Okay, so this explicitly tests this coefficient to see if it's insignificant, right? So my B33, which is a negative 0.750, right? This blue thing, it's an estimate of beta 1 up here, right? It's an estimate of this beta 1. And I'm subtracting off the hypothesized value, right? The hypothesized value here is 0, right? And then I'm going to divide by the standard error, right? And I get the same T-stat that I had before, right? I'm getting the same statistic I had before. Okay. Now, I'm going to use critical values to do this test, but I could use p-values as well, right? So I'm going to use Excel. Let me pull stat distributions.com up. Stat distributions plural.com. Yep. Now, this is the estimated standard error. Because we're using an estimate of the standard error, we have to use a t-distribution. Okay. So first thing we got to do is we got to change this to a t-distribution up here. We want to do students t distribution, right? The degrees of freedom are going to be this 5 right there. Degrees of freedom will be 5. Okay. And my significance level is 0.05, right? I have a 0.05 significance level. That should be 0.05 there. This blue shaded area is the significance, right? Half of significance is to the right of this value. Half of that significance level is to the left of its negative, right? So this is a negative right here, a negative 2.571. So this blue area is 0.025, and this blue area is 0.025. You add them together and you get 0.05. That's our significance level, right? So our critical value is 2.571. Right? I'm going to verify that because statdistributions.com, sometimes when the degrees of freedom are low, it doesn't get quite close enough. So let's go into Excel. I'm going to get 2.571 here. I'm going to type t dot inverse, right? T dot inverse. My alpha level is 5%, right? Alpha level is 5% or 0.05. And it's a two-tailed test, right? That's a two-tailed test because the alternative hypothesis is beta 1 is less than 0 or it's greater than 0. Beta 1 is less than or greater than 0. Another way to say it is beta 1 is not equal to 0, right? So this is a two-tailed test. So when I have a two-tailed test, I have to divide my significance level by 2. Then I got to do the degrees of freedom. The degrees of freedom again are 5, right? Degrees of freedom are 5. The error degrees of freedom are the degrees of freedom of this test statistic. Distribution. Use 3 decimals places. And notice that I got a negative 2.571, right? This value right here is a negative 2.571. We got symmetry, right? So the upper critical value is a negative 2.571. The upper critical value is a positive 2.571. So notice it says plus or minus right there, right? Plus or minus 2.571. Those are our critical values. Now, this is a 5% significance test, right? If my test statistic is out here, or my test statistic is out here, then I say the difference, my difference between my estimated coefficient, in my case, negative 0.750, the difference between that and 0 is significant, right? Why do I say that? Because the test statistic is under the blue area, and the blue area is called significance. Now, here's the catch. Here's the rub. Your estimated beta and 0 are going to be different. The probability that your estimate of beta and 0 are equal is the probability that being true is 0. Why? Because there is one value 0 on the number line. There's only one 0 on the number line. There's infinite many values that beta 2 could be. There's infinite many values that beta 1 could be, right? So the probability of your estimate for beta 1 being equal to 0, well, that's 0, right? So the thing is, there's going to be a difference, right? There's going to be a difference between what you estimate for this parameter and 0. There's going to be a difference between what you estimate for this parameter and 0. so there's going to be a difference, right? Maybe slight negative, slight positive, maybe massively negative, maybe massively positive. There's going to be a difference. The question is that difference significant, right? Is that difference significant? And our significance level here is 0.05, right? So graphically, this blue area is significance. This blue area is significance. There's going to be a difference. So the probability of us being at 0 is 0, right? So we're going to have a slight positive difference or a large positive difference. Or we're going to have a negative slight difference, or we're going to have a massive negative difference, right? Because my test statistic falls under the negative, it falls on the negative side of this distribution. It's over on the negative side. And the test statistic is huge in absolute value, 7.536. We're way out here, aren't we? We're way out here somewhere. It's really highly significant. Highly significant. So the difference is negative, and that difference is significant, right? Because again, we're under the blue area, and the blue area is significance. So, if that difference between the estimated parameter and 0 is significant, right? Then we have evidence in support of the alternative hypothesis, right? If our test statistic is close to 0, we're under the white area. And we would say the difference between our estimated slope and 0 would be insignificant, right? And we would have evidence in support of the null hypothesis. So this region under the white area is the do not reject the null region. The area under the purple significance level here and here, that's the reject the null region. So for lobster price coefficient, we're going to reject the null. Okay, so because the null hypothesis of the test of coefficient of significance is rejected, that's a massive, an absolute value that's huge, right? Almost 8 standard deviations below 0, right? So that's a massive test statistic in absolute value. We're going to reject the null hypothesis. We're rejecting this, right? We're rejecting that. So the price of lobster has what? Well, one has a significant effect, right? So it's either this one or it's that one.
It has to be a significant negative effect because if
Exactly.
the number's that big, then yes.
Yep, exactly. So it's because it's negative, it's got to have a negative effect, right? But because that test statistic is so large in absolute value, it's going to have a significant negative effect, right? Cool. What about average customer income? Average customer income, its test statistic is small, isn't it? It's small. The test statistic is small. It's under the white area, right? So what we're saying there is this coefficient, look at its number, right? It's negative 0.001. It's close to 0, isn't it? And its difference, the difference between negative 0.001 and 0, there's a difference. But that difference is insignificant because the test statistic is under the white area, not under the blue significance area, right? So this suggests that the null hypothesis is true, right? We can't say the null hypothesis is true. We can't accept a null hypothesis, right? So what we say instead is we say we cannot reject the null hypothesis for average customer income. Again, this test statistic is small, right? And the smaller the test statistic is, the closer it is to 0, more insignificant the slope coefficient is, right? So here we're going to say cannot reject or not rejected, right? So on this one, I'm going to say a negative effect, right? I'm going to say a negative effect because my coefficient is negative. You might have a positive effect, right?
But even if it was negative, wouldn't it be insignificant?
Yeah, right. So mine's negative, right? So only these two work for me. But in addition to being negative, mine's going to be insignificant. Okay. Okay, so we got everything good. With the exception of my hiccup right here, this is actually correct, right? With the exception of that, everything looks good, right?
I have a
Now we're gonna,
question
yeah, Quaimar.
for the so for my T statistic on the price of lobster, mine's negative 3.935, and
Yeah.
my critical value was 4.032.
Oh, because
So
you have a
mine lands in the white space.
yeah, you have a significance level of like 1%. Is your significance 1%? 0.01?
Oh yeah.
Yeah, okay,
Uh,
that's why, right? Yeah, so yours would be insignificant, negative, right? So typically what most businesses use, they use 5% significance. And if you're selling lobster, 5% significance is good. If you're selling a vaccine, maybe you want to use 1% significance, right? So if your product can kill people, maybe play it safer and use a smaller amount of significance, right?
Like 0.01?
What was that, Craig?
You said use a smaller significance, like I just said 0.01 or
Yeah,
something?
like if you're testing whether a vaccine works or not, maybe you want to use a smaller amount of significance like 0.01, right?
Okay.
So the difference, the effect has to be really big, right? The effect has to be highly significant for you to go, yeah, it's good. Let's prove the medicine, right? Because the first rule of medicine is don't do any damage, right? So if it's a vaccine, maybe you want to use 1% significance. But if you're counting the number of chocolate chip cookies or count the number of chips in a chocolate chip cookie, 5% significance is great, right? But in business, in most business situations, I think people are probably using 5% significance. Okay. And it does affect your results, right? It does affect your results. I mean, I should say it does affect your conclusions, right? On the significance level that you use. Quaimar, if you're sorry, I had a glass of milk before I started. If your significance level is 5%, then you would have had the same conclusion that Quaimar or Craig and I had, right?
yeah.
Yeah, you would have the same conclusion that we had, right? But yours is you're using 1% significance. Basically, a really small significance level means the burden of proof is really stringent. You have to really you're wanting the person to come with overwhelming evidence, right? Overwhelming evidence, right? So your test is very stringent, right? I would say the burden proof is much larger in your model than in our model, which is only 5% significance, right? You can think of the hump of the distribution as the burden, right? You can think of this as the burden. And you're way out here, right? You're way out here. So your critical values, right? There's a huge hurdle for you to overcome to conclude that lobster price affects in a negative way how much it's sold, right? And in business, frankly, you don't need that big of a burden of proof for the most part, unless you're making peanut butter and you send your peanut butter off to a lab and they're testing for E. coli, right? There's a big case in Georgia where a peanut butter lab was shopping around and was trying to find a lab that would certify its peanut butter free of E. coli. So, I mean, if it's something that can kill your customers, then you want to have really low significance. But if it's counting the number of chocolate chips in a cookie, then 5% significance is fine. All right, so the next thing we have to do is we have to test whether the model is significant. Now, notice how the hypothesis changes. Notice how that null hypothesis changes. What does this say right here? It says both slope coefficients are 0 simultaneously, right? That's what that's saying right there, right? Both are simultaneously 0. Right? So this right here, this test statistic here, it can only be used to test whether this lobster price coefficient, right? This one is used to test this customer income coefficient. The F statistic, I'm going to call it F stat. The F statistic is the statistic that you use, test statistic that you use to determine if both are equal to 0 at the same time. They're simultaneously equal to 0. They're both equal to 0, right? That use the F statistic for that, right? So what I'm going to do is I'm going to get the critical value here. You can use this formula to get the critical value. I'm going to put it right here. The 0.05 is your significance level, right? Your significance level is at 0.05. In your case, QIMR would be 0.01, right? The DFR, this is the degrees of freedom of regression. That's 2, right? And the DFE, that's the degrees of freedom for the error, which is 5. Okay? And in reality, we call this the degrees of freedom of the numerator. We call this the degrees of freedom of the denominator. The reason why we do that is because, remember, this value here is the ratio of our sum of squares to regression divided by our regression degrees of freedom, right? See that? So the ratio of these two, right, gives us our mean squares. Okay? And then the F stat is just the ratio of these mean squares. Okay? What happened? Oh, got a comma in there instead of a division sign. Okay, so this estimate of sigma is in the numerator and has degrees of freedom of 2. This estimate of sigma is in the denominator and it has the degrees of freedom equal to 5. So that's why this is called the numerator degrees of freedom. And that's why this is called the denominator degrees of freedom, right? So my F critical value is 5.786, right? I can get that in statdistributions.com. So I click on F here. My degrees of freedom in the numerator, my numerator degrees of freedom are 2. My denominator degrees of freedom are 5. Okay. And my p-value, or my significance level is 0.05. And my critical value is 5.786, which is the same as what we got in Excel. right? Now the question is the F-stat on the right side or is it on the left side? If it's on the left side, then collectively, these are the differences between these coefficients and zero. Those differences are insignificant collectively, right? If the F-stat is on the right side under the significance level, then collectively the differences between these values and zero are significant, right? So the difference between these values and zero on a collective basis are very significant because our F-stat is huge. Mine's 32, right? So again, the white area, if you're under the white area, that's I cannot reject the null region. Under this blue area, that is reject the null, right? So we're going to reject this null hypothesis. We're going to reject this hypothesis here. Now that makes sense. Why? Well, this right here suggests that not all of these slopes are zero, right? That's what this suggests, right? So that's why rejecting this makes sense, right? So the critical value of the test is 5.786. The F statistic from the ANOVA table, mine, to 3 decimal places, is 32.013. My conclusion is that because the null hypothesis of the test of model significance is, in my case, rejected, which makes sense because we rejected this being zero, right? We couldn't reject this being zero, but we could reject that being zero, right? So at least one of them is probably not zero, right? At least one of them appears to be different than zero. So that's why rejecting here makes sense, right?
Okay, but in my case, look like the numbers are not too far apart, as in it's the critical value is 13.274, and the F statistics only marginally higher. So
You'd
wouldn't
still be in the
the
rejection region. You'd still be in the rejection region.
okay, I just wanted to ask.
Yep.
Yeah, I just wanted to ask.
Okay. Yeah. Okay. Yeah. All right. Cool. Yeah. If you're into the rejection region, you reject. Okay. So our model, this is our model here, right? That's our model. It's linear in lobster price. Quantity of lobster demanded is linear in lobster price and customer income, right? And we're estimating this beta 1 and this beta 2, right? And all we're saying here is the model is significant. And again, we're saying it's significant because why? The F-stat is under the blue area, right? We're under the blue area, and the blue area is significant, so the model is significant. Okay. Now, Blue Lobster Bar and Grill charges a price of $35. So I'm going to go back up here. I'm going to change this to red. And I'll go bold, right? So Blue Lobster Bar and Grill charges a price of $35. So our lobster price is $35. And average income of his customers is 2,066. Right? Restaurant expects to sell how many lobsters? Again, how do we get this number right here? This is called deploying the model, right? We're deploying the model. We took this $35 price, right? We took the $35 price and we multiplied it by the slope coefficient for lobster, right? Minus 0.750 in my case. Then we added what? We added this customer income, 2,066 in my case, times the income, customer income coefficient. And then the last thing we did is we added the intercept, right? We added the intercept. So we took this blue box times this red box, add that to this purple box times this green box, and we added this maroon box, right? And we get a value of 74.843, right?
Can you bring that equation back? I didn't put that equation in the first time that you did it.
Yep.
I thought it was just like you showing us how to actually work it out. So I didn't put it in.
So I have my predicted values here, my errors here, right? And then I have my squared errors here. Yeah. So these are my squared errors. Right, those are my squared errors. So what I did here is underneath my lobster price, right, I tapped at 35. And notice it's pretty close to my lobster price average, right?
Uh-huh.
And then I have customer income, which is really close to my customer income average, right? See that?
Uh-huh.
So these are my means, and I'm saying suppose my lobster price is about average, and my average customer income is about equal to the average, right? So I got 35 and 2,066. Those are from right here, right? Now I want to calculate the predicted quantity demanded. So what I have to do is I have to multiply this 35, in my case, C10, right? C10 is this blue box around 35. I got to multiply that by B33, right? B33 is my lobster price coefficient. See that?
Uh-huh.
And then I got to add to what? I got to add to that, right?
Yes.
And I'm adding what? I'm taking the customer income and I'm multiplying it by what? The customer income coefficient, right? The customer income coefficient, this number in this green box right here, right? And the last thing I'm doing is I'm adding the intercept of the model, right? The estimated intercept right here.
Excuse me, sir. If you do not mind, I'm gonna go ahead and go and leave because I've got the green on this question.
Okay, cool, awesome. Yep.
Okay,
Have a good night.
One more thing.
Yeah.
Is it okay if we actually meet at office hours on Wednesday? I'd like to go over one of the homework assignments.
Yeah.
I'm having trouble.
10 to 2. Yeah.
All right. Great.
Yeah.
Thanks.
Okay, no problem. All right.
Bye.
Marge, get it?
What was the last one? So after I added the number from the customer income and multiplied that by the customer income,
The last one
what
is
was the last thing to add?
the intercept. The estimated intercept, the third number here, right? And you don't multiply this by anything because it's just the intercept of the model, right? So you take the lobster price times this coefficient, customer income times this coefficient, plus the estimated intercept, right?
Mm-hmm.
Okay, you got it? It should look pretty close to the other numbers, right? It should look pretty close to the other numbers.
Charger price of 41. Okay.
You got it? You want to share your screen if you don't have it?
I got it.
Oh, you got
I
it?
was
Okay.
just yeah, I was putting the equation in, but I didn't have my numbers in the lobster price box and the customer income box at the top. So I
Okay.
just put the equation in, and then I had to go back to my question to get the values.
Okay, cool. Awesome. Right. Now, notice what happens. We're going to hold constant everything else, but we're going to increase the lobster price, right? I'm going to increase it 36. What happened to my predicted quantity demanded? It went down, right?
Mhm.
Which is the law of demand, right? You're learning that in
Yeah, I
economics?
believe so.
Yeah. Now, what is this difference equal to right here? What do you think that difference is equal to? I don't even have to do it in my head. This difference right here in these two, the lobster price increased by $1, and this increased by or decreased by how much? If you calculate the difference in these two,
750.
yeah, if you calculate the difference in these two predicted values for lobsters sold,
Mhm.
you'll get that value, right? Why? Because
Mhm.
what is the slope? Well, the slope says if I increase the lobster price by $1, rise over run, right? The rise is the change in quantity of lobster. The run is the change in lobster price. So if I increase the lobster price by $1, my expected sales of lobster, in my case, will drop by 0.75. And notice here, if my customer income increases by $1 or $10, right? My lobster sales will go down by 0.001 or 0.01, right?
Mhm.
I'd have to, in order for this to have an effect, if I multiply this by 1,000, right? Now, if I multiply this value right here by 1,000, what that means is if my income goes up by 1,000, right? If my income goes up by 1,000, then what's going to happen to the number of lobsters sold? It goes down by 0.6, right? So let's do 10,000. If my income goes by 10,000, right? Then my lobsters sold to go down by 6.5. Now that's a huge amount of money, right? It's a
Mhm.
huge amount of money uh, for a 2-week period, right? Huge amount of money. And you're having a very small effect on that large change in customer income has having a very small impact on customer income, on lobster sales, right? Why? Because, it's insignificant, right? This is basically zero. Both this and that in magnitude is close to zero. And the T-stat is saying, well, this thing that's close to zero is statistically indistinguishable from zero, right? So customer income is having a very small effect, very tiny effect, tiny effect on the number of lobsters sold. Probably because rich people, they probably eat a lot of lobster. And their income goes up a little bit. Are they going to eat any more? Probably not, right? I would think though, for poor people, people on the lower end of the income distribution, I think their income would have to go up a lot for them to buy lobster, right?
Mhm.
So to me, that this kind of makes sense, right?
Yeah.
for poor people, if their income goes up a lot, they're going to want to buy more lobster because they're not eating any lobster when they are poor, right? But when they get a bunch of money, maybe they get a big check from a refund, check or something from the government at the end during tax season. They might go out and buy lobster, right? Rest of the year, and they're not. But a really wealthy person, well, they're probably already eating a lot of lobster, right? If their income goes up, they're not going to eat any more, right? They're already eating a lot of lobster. So I think customer income probably is non-linear in the quantity of lobster sold, right? It's probably parabolic, right? It's probably a quadratic where quantity demanded of lobster would go up at low incomes and then peak out at higher incomes. So it's probably quadratic. It's definitely non-linear, I think. Yeah. Okay. Any questions?
No, sir.
All right. Well, have a good night.
You too.
All right. Bye.